NASA is preparing to build the first sustained human outpost on another world, the Artemis Base Camp at the extreme lunar South Pole. Looking at this map of the Noble Rim region, you can see the exact target zones marked by these red pins. NASA is hunting for permanent shadow regions, deep craters where ancient ice deposits remain frozen under the surface. Extracting that ice means operating in a brutally unforgiving environment. The lunar surface is coated in a fine, glassy dust. These ultrafine particles are razor-sharp, highly abrasive, and will easily shred spacesuit seals or completely lock up mechanical joints. Then comes the darkness. The lunar night at the South Pole plunges the region into a freezing void for more than 100 hours at a time, instantly rendering standard solar power arrays useless. Constructing a long-term habitat here presents an engineering nightmare, keeping a high-tech facility alive while the environment actively tears at its structural and thermal limits. Surviving this requires discarding the idea of a passive shelter. The infrastructure built for Artemis must be able to diagnose itself, adjust to extreme temperature swings, and make life-saving decisions entirely on its own. That self-reliance begins before you even reach the surface, aboard the Habitation and Logistics Outpost, or HALO. This is the first habitable element of the Lunar Gateway, orbiting the Moon. HALO houses the Primary Environmental Control and Life Support System, or ECLSS. Because Gateway is positioned in a deep space orbit, communications with Earth face significant delays. Ground control cannot instantly intervene to fix a sudden oxygen leak or thermal failure. To keep the crew alive, the ECLSS is built with layered autonomous failsafes. If the system detects a failure in the main pressure response lines, it immediately reroutes the air supply using a network of dissimilar backup valves. Even the carbon dioxide scrubbers can automatically increase fan speeds to compensate if another module scrubbers go offline. These routines run continuously, managing the station's atmosphere through long months when no astronauts are on board. HALO operates as the central nervous system for the entire orbital stack, guaranteeing a breathable, pressurized safe haven without needing a single human keystroke. Down on the lunar surface, the anchor of the Artemis Base Camp requires that same level of independence. This rendering shows the core of that camp, the surface habitat, towering above the rovers and equipment around it. Looking at the habitat schematic, you see a hybrid structure, a rigid metallic core topped with a massive inflatable living section. To survive 100-hour periods of darkness, regenerative fuel cells near the solar arrays store daytime power to keep systems warm when the sun disappears. This thermal regulation is vital for what engineers call dormancy. Because the habitat will be left empty for months or even years between missions, it has to prevent its own thermal fluids from freezing solid, while deploying automated sensors to detect and scrub out microbial growth. It also acts as an automated utility hub. When a pressurized rover docks, the habitat takes in the rover's wastewater, processes it through its own life support systems, and pumps fresh, breathable oxygen and potable water back into the rover's tanks. The surface habitat functions as a closed-loop mechanical organism, engineered to endure total isolation on the lunar South Pole. Outside the habitat, the physical labor of the base falls to a fleet of autonomous quadrupedal robots equipped with mounted manipulator arms. Instead of relying on delayed remote control from Earth, these robots learn to walk using a method called constrained reinforcement learning. They are placed in a simulation and forced to teach themselves how to navigate. This diagram maps the robot's brain. The policy network takes state observations and outputs joint positions into the simulation. Crucially, a reward and constraint manager feeds back into the algorithm, applying strict mathematical limits so the robot never exceeds maximum torque or loses balance. Because the machine learned to walk under these strict constraints in a simulated low-gravity environment, it dynamically adjusts its posture in the real world, catching its balance on steep craters or loose regolith. This machine learning approach removes the need for a human pilot entirely. The robots have developed their own physical intelligence to survive the terrain. This graphic outlines the true scale of the Artemis architecture. We are talking about billions of dollars invested in orbital hubs, complex surface habitats, and highly mobile robotic explorers. But if you look closely at the mission logistics, there is a stark reality to this massive infrastructure project. astronauts will only be physically present on the lunar surface for 30 to 60 days at a time. For the remaining 10 months of the year, there are no humans. The base sits entirely empty. It operates as a high-tech ghost town, maintaining its own pressure, regulating its own temperature, and conducting research, driven entirely by code and machine learning. NASA's goal is a sustained human presence on the Moon. In reality, the permanent residents of the Lunar South Pole will be the machines.